Thank you very much for the introduction, Max. My name is Detlef Koschny. I used to work at the European Space Agency. I retired from the agency at the beginning of the year. I did not retire from work. I continue working on asteroids, meteors, fireballs, now from the Technical University of Munich. I also have a position at the Space Exploration Institute in Neuchâtel in Switzerland, working on the ExoMars mission. Today, I'm going to talk to you about a hobby that I started 3 years ago, namely to look at lunar impact flashes. And the first thing I want you to realize, how would a lunar impact flash look like? For that, you should close your eyes, please. I did not bring a video. Close your eyes, visualize yourself in your favorite location. You have a nice horizon. You see the moon and you see this thin crescent of the moon, just like in the picture that you saw a minute ago. And the dark side of the moon, and I call it dark side, it's the unilluminated part. It's not really dark. You see some ashen light there. And now just visualize a star-like point appearing shortly and going away again. All right, you can open your eyes. That's how a lunar impact flash looks like. All right. It didn't bring a video, so I had to do it this way. But, I think it worked. And the real question, the scientific question is, who cares? And the interesting thing is the reason for this flash is the same reason that we see a meteor in the Earth's atmosphere. It's a meteoroid, a small object in space in the solar system. Only instead of entering the Earth's atmosphere, it hits the lunar surface. And just when it hits, it sort of converts its kinetic energy. Part of it becomes a crater. Part of the energy goes in heat. And the heat is so high that you actually emit light. And that was the flash that you saw inside your eyes. Now, scientifically, it's interesting because the objects that we typically see with ground-based observations are centimeters, decimeters, maybe a meter in size. That's the typical size range that you can see. And I indicate that here in this blue plot. That's from a paper we did a few years ago, where we basically put together all the known flux densities over the mass ranges or size ranges that we have ever measured, from micron-sized dust up to many kilometer-sized asteroids. And what you see here, what you almost don't see it, is that the uncertainty in the number of objects here is still quite large, in particular in this range. And if you go to the left, it's actually almost 2 orders of magnitude. So if I tell you, okay, a 1 meter object will impact the Earth, say typically every year, it could be every month, or it could be every 10 years. That's the uncertainty we're talking about. To reduce this uncertainty, we need more data. I quote Galina. And one of the ways to achieve this is to add this huge collection area of the moon to our area that we look at and analyze. So that's the scientific background. Now, how do you do this? I started doing this a few years ago with the equipment I had at home. I'm using a 10-inch Newtonian. In Germany, I have a 12-inch, doesn't really matter, almost the same size. And here you see the telescope. You need to track the moon somehow, or even better, guide the moon. If you're too lazy to properly align your mount, that's one of the challenges, actually. The moon does not follow the stars. It moves across the stars, obviously. It also moves north and south. Most of the movement is parallax. It's because the stupid Earth is rotating and not sitting still. And that means you need to correct for that. I do this manually. So, I spend 5 hours in the garden walking around, and every 2 minutes I press the north or south button, get lots of exercises, 10,000 steps every night. Here you see the moon. Another setup I was using is a refractor. It turns out, if you read papers about this, people say, oh, you can do this up until 50% illumination of the moon maximum. If you have more, you cannot see the flashes anymore because of stray light. That just shows that the papers were written by people that have very bad telescopes, because if you have a telescope with good stray light rejection, you can go much further. Unfortunately, also my telescopes are apparently bad according to my definition. If you have a reflecting telescope, it's very, very difficult to baffle them properly. With a refractor, it's much easier. Unfortunately, then, of course, you lose aperture because for the same money, you get only much smaller refractors. So there's a bit of trade-off space. It also shows that there is room for every telescope. If you have, you know, a 13-centimeter refractor, you observe during a meteor shower, chances are that you see something. There were papers published using data from telescopes as small as this one. You want to record the moon with, say, video rates of many frames per second, because these flashes are typically very short. They're just tens of milliseconds. Only the very bright ones are really longer. The longest ever was 8 seconds, which was recorded by Spanish colleagues many years ago. But typically it's, you know, in a video recording, it's 1 or 2 frames, something like that. I also use a 6-inch refractor. Okay. How many of these objects would you expect to detect? Well, it depends on the sensitivity of your telescope, and of course also it depends on the stray light. I didn't do a detailed analysis, but just to get an idea of how long would you have to wait on average for an impact flash, I took all the observations that were collected by a professional program, the Niliota project. There should be a link somewhere in the end. No, the link is actually here. They have been observing the moon with a big telescope, 1.2 meter telescope. They were using front illuminated cameras for recording. So it's, you know, it's a big telescope. It goes very faint. The faintest flashes they were seeing are, say, 11 or 12th magnitude. And this is the cumulative number of events brighter than a given magnitude for the 271 hours they had been observing when I did this plot, which was, I think, a couple of weeks ago. Now it's, I think, 278 hours. And you see in total, they saw something like 270 events. So they have typically 1 per hour. Here on the left, I show if you have a telescope that would record a flash brighter than 8 magnitude, on average, you would need to wait about 5 to 6 hours to see something. Now, take note that I did not bother here to separate between sporadics and stream meteors. So obviously, during a shower, when we have like the Perseids, then the meteoroid stream would also hit the moon. You would expect more. Whereas the sporadics, if you observe between streams, you would probably have to wait a bit longer. For 9th magnitude, this is where I think I can see with my 10 to 12-inch telescope. Remember, this is video, so you have short exposure times. You would need to wait on average a few hours. So it's a good complementary thing, because when the moon is up, normally you don't really want to bother with visual meteor observations. So if you're a visual meteor observer and have a telescope, when the moon is up, point the telescope at the moon. How do you detect these flashes? Well, you can record the video and then go through it frame by frame. This is how we started meteor observations. When we did the video recordings of the meteors, so remember for the Leonids, we were recording on videotape, and then we were using MetRec, but we didn't believe it. So we also watched the video manually. Okay, these times are long over. Here for the impact flashes, this is exactly where we stand right now. There is detection software. This one is one. It's an open source software which was developed by this Greek team, this professional team. Software is not perfect yet. It needs improvement. I don't believe that it detects everything it could detect. So, but this is where we are. It's like 20 years or 30 years ago in meteor astronomy. Quite interesting. This is how the software looks like. It's actually a plug-in to Fire Capture. Who knows Fire Capture? Yeah, okay, some people do. That's a freeware, not open source, but a freeware tool that you can download for recording. Mainly it's meant for video recording of astronomical targets, and it allows plugins, and we have a plugin which is called this flash detection software, which is what I call a real-time quick and dirty detection. So it will give me over an hour, say 50 detections, and most of them will be wrong. But then there's an offline tool. This is simply to avoid that I record terabytes of video data. And I mean, I run out easily of disk space here. Disks are always a factor of 1,000 too small. I mean, we know that, and this is a constant. So a terabyte is nothing if you record a video here uncompressed. This software, and this is a discussion that Peter always comes up with, does not currently support these compression formats that you would have for consumer cameras. That's something we'll have to add. But then there's an offline detection tool, which takes the data stored by this plugin and goes through it in detail and says, okay, this was a moving object, so it's a satellite, or this was just 1 pixel, so it must have been a cosmic, and that should help doing this. If you want to use it, contact me, because the step from real-time to standalone means that you need to fix some things which the developers didn't think of, and there are additional scripts that you need to use for that. So it's just the beginning. Another thing I started a while ago is I came up with a form sheet, again, in the tradition of our meteor observations. I'm interested in these flux densities. I mean, other people say, I just want to see whether there's a fresh impact crater that was formed, comparing it to data from the Lunar Reconnaissance Orbiter, for example. If you want to understand how many there are, again, it's very similar to the meteor astronomy field. You need to know when you started observing, when you stopped observing, were there clouds in between, what's your limiting magnitude, was there fog or something like that. So there's a form sheet for that that I came up for myself. And if I don't follow it, I keep forgetting things, and then I bite myself somewhere because I forgot something. But if I use the form sheet, it's all fine. We also have a simulation tool which simulates impact flashes. Here is one. It generates videos, or you can just display a simulated lunar view on the screen. This is something we're using, or I'm using right now for, well, there's a lady in Greece that does the same thing to test this detection software to see, does it really see everything? It's difficult to test this looking at the sky because you have to wait so long. So it's quite a boring thing. Whereas here in this simulator, I can tell it, well, generate me a flash every 5 seconds with different brightnesses, and then I can see how this detection tool works. This is a statement that I keep making everywhere, both to professionals and amateurs. Here you see the moon through my refractor, and this is well over 50% illumination. I can still see the ashen light here, which also means if I reduce the gain, I wouldn't operate the camera like this for impact flashes, but then I would reduce the gain, so I have more dynamical range. But that shows that you can see something here. Of course, there's stray light. Of course, it's better to go to space where you don't have the atmosphere and you want a perfect telescope. So you pay 2 million or something to a professional company. But okay, I didn't do that. I'm using my off-the-shelf equipment. It's possible to do much more than 50%. Why do you want to do that? Because, you know, the best is what I showed in the title slide. You have this thin crescent and most of the moon is dark and there's little stray light. How long does the moon stay above the horizon if I have the situation? Well, half an hour or so, because it's close to the sun, so it will set shortly after the sun or only rise shortly before the sunrise. So that's why I keep telling people, consider observing for longer times, even when there is more illumination. Okay, just a video here. You see how it looks like with different gains, and this again, I think this is with the reflector. So at this lunar phase, stray light is okay. One thing, I mean, this is meant to be an overview for you, and the paper in the proceedings will give you lots of links where you can get started to inform yourself about the topic. So it's one of the things which is relevant here is there is a space mission which is actually funded up until launch and operations by the Italian Space Agency. It's an ESA mission, and it's a Cubesat, so it's built of these little 10 by 10 by 10 cubic centimeter blocks, and it's 20 by 20 by 30 centimeters in total. The main or the only payload is a camera. And it's meant to observe now the far side of the moon. So the side away from the Earth, from the back of the Earth, so to say, to complement ground-based observations. This is in phase B now, as we call it. There's something called the preliminary design review next month. And then after that, they will actually start building hardware. There's also already some test hardware, and the launch is meant to be in 2026, 27. We're still finalizing the launch opportunity. It will then spend 2 weeks observing the dark side of the moon from behind, so the dark part of the far side, and that's going to be really dark because there's no reflected light from the Earth, and we're in space, so there's no stray light from this stupid atmosphere that only bothers us with that. Well, not from meteor observation. It's quite useful to have the atmosphere. Okay, I didn't say anything. And then, yeah, thank you. The other 2 weeks, this is the science cycle when we look at the dark part. And the other 2 weeks, they use this for engineering activities. And I keep pushing them. I say, look, why do you stop at 50%? Let's go a bit further, even if the illuminated part of the moon is higher and we see less area. So we're still working on that. Right, lots of text here. I just wanted to remind you, some of you were participating in the series of Europlanet workshops that we had over the last 2 years, where we brought together the Fireball community, people talking about artificial intelligence or machine learning in meteor detection. And later, we also worked a lot about lunar impact flashes. Here, again, this is for your record, more or less. Look at this at your leisure. There's a link where you can find all the presentations of these workshops. So if you're interested to learn more, go there. That's all very recent and shows you all the people that are currently working in the field. There is one big project in Europe. Actually, there was one big project, I should say. Niliota is a Greek project. Forgot what this stands for, but the NE is probably near Earth object or lunar impact something. They observed impact flashes for 6 years. That's what I showed you before in this magnitude diagram, about 1 per hour. So they had roughly 2,700 hours of observations, 270 flashes. But the funding has stopped a few months ago. You know, you leave the agency and funding stops for these things, stranger. But no, but there is a plan for continuing. It just hasn't happened yet. The ASI or ESA ASI space mission, which I just mentioned, called Lumio, they have something called science working groups. There was a call out a while ago. We now have science working groups established, and here is a link to the call. There's no dedicated web page yet, but I want to point you to the name of Tony Cook. Some of you may know him. He's very active in the British Astronomical Association and running the lunar impact flash activities from the British side. Here's a link for this detection software and simulation tool. And I just had a student starting on developing a lunar guider. So you can track the moon if you have some software that knows where the moon is and points it and keeps the moon in your camera field of view. Doesn't work for me because I'm never bothering to align the mount properly. So I need a guider actively. It doesn't work with the normal guiding software that you have for stars because it's an extended object, but hopefully in a few months we will have something there. NASA, of course, has been operating an impact flash activity for many, many years. That is currently focusing on meteor showers or meteoroid streams, I should say. So they don't observe regularly like Niliota did, but still do a lot of good stuff. And in ESA, there are currently new players emerging. There's a Polish company that operates telescopes in Italy, and they're just now installing 2 RASA 11-inch telescopes to look at the moon and record the dark side of the moon from Italy. Brian Kudnick from ALPO in the US has set up an email group. So if you're interested in, go to this link, groups.io, and Google for lunar impacts. The Observatoire Nice is very active there, and they do something cool also together with Tony Cook from the BAA. 1 minute. They look at infrared cameras. The Italians are active. And okay, you know, I think the message is if you have a telescope and camera, go out there and start observing meteoroids. This is an impact flash, which could be one. I'm not sure. It's a flash in my recording, just one frame. And I had coma here because I did not use a coma corrector to avoid stray light. The stars look similar. They look more in one row here. I see these two peaks. But this is how it could look like. I'm not sure what it is. You'll hear more about this in the next presentation by Beta. Normally, we say you need an independent observation of the flash to be really sure that it's one. But this is how it could look like. And that was me with more hair. So thank you very much for your attention.